Namaste. Welcome to the next video of Machine Learning Techniques course. In this video, we'll implement variations of gradient descent algorithm, mainly the mini-batch gradient descent and the stochastic gradient descent. Since we are going to implement these algorithms from scratch, we are going to need some basic Python libraries like NumPy. We'll import them through the import library cell. Then we need a bunch of helper functions from our previous collabs for generating training set, preprocessing the training set, the model inference, loss calculation, partial derivative of loss calculation, and weight update functions. We'll also need a function for plotting learning curves. Let's first generate the training data containing 100 examples. We'll pre-process the training data to obtain training and test splits. We obtain training and test feature matrices and train and test label vectors. Let's first implement mini-batch gradient descent. The key idea in mini-batch gradient descent is to perform weight updates by computing gradient on batches of small number of examples. You may remember that one of the most time consuming step in gradient descent was the weight update step. It involves calculation of partial derivative, which needs to be done by summing up over all the examples in the training set. So if you have training example containing millions of examples, then the weight update is generally slow in case of gradient descent. We try to address that problem by using batches of small number of examples, and we perform the gradient computation on the small number of examples at a time and perform the weight updates. For mini-batch gradient descent and stochastic gradient descent, we need a function for defining a learning schedule. The learning schedule gradually decreases the learning rate of both these variations. We initially start with larger learning rate, and then the learning schedule will gradually decrease it as we make iterations through these procedures. You can see that the mini-batch gradient descent is very similar to the gradient descent algorithm. It only differs in selection of a small number of examples. So this part of the code that you see here deals with selection of a small number of examples. We initially shuffle the training set and get a small, and basically on this particular shuffle training set we iterate with the size of the specified mini batch, and at a time we take number of examples equal to the mini batch size and then perform all the operations like gradient descent. We first perform the gradient calculation followed by the weight updates. This is the weight initialization step here, and we use some of the variables like w_all and error_all for bookkeeping purposes, just like in gradient descent implementation. The weight_all stores weight vector across all the iterations, and error_all stores errors across all the iterations. Let us test the mini-batch gradient descent algorithm with the synthetically generated dataset. The advantage of that is that since we know the weight vector by which data was generated, we can test the weight vector obtained from MBGD or mini-batch gradient descent with the actual weight vector that was used to generate the data. So we set up the test with feature matrix and label vector corresponding to the synthetic data, and the expected weight vector is the weight vector that was used to generate this data. We call the mini-batch gradient descent function and we obtain the final weight vector along with error and weight vector for all the iterations. We test the obtained label vector. We first test its shape, whether it has got two values or not, because we are currently solving the problem with a single feature, and for single feature we have two weights, one for the feature and second for the special feature which is x0. And we also check whether this particular weight vector is almost equal to the expected weight vector. As you can see, the test passes for this particular setup. Let's look at the learning curves for the mini-batch gradient descent. We use errors across all the iterations for plotting the learning curves. You can see that so we run the mini-batch gradient descent for 20 epochs with the batch size of 8, and you can see that the loss is gradually decreasing across different iterations. You have iterations on x-axis and loss on y-axis. Now let's implement the second variation, which is stochastic gradient descent. Stochastic gradient descent is exactly like mini-batch gradient descent, except that we use the number of examples per batch is equal to 1. So the key idea here is to perform the weight updates by computing gradient on one example at a time. And you can see that here we randomly, so this is where we initialize our weight vector. These are two variables that are used for bookkeeping. We have talked about them in gradient descent and mini-batch gradient descent implementation. And here we run the loop for the specified number of epochs, and in each epoch what we do is we run it for the size of the training set. We run the inner loop for all examples. So x dot shape 0 gives us the size of the training set, and this inner loop is run for the size of the training set. And inside inner loop we first randomly select an example and we perform the weight update on that particular randomly selected example. So we first calculate the gradient, update the learning schedule, and then update the weight vector, and then we append the error for this particular step and the weight vector obtained in this particular step in the respective variables. Finally, we return the final weight vector, errors across all the iterations, and weight vectors across all the iterations. Just like gradient descent and mini-batch gradient descent, we also test the stochastic gradient descent with the synthetic data. So we set the feature matrix and label vector equal to the training set obtained from the synthetic data. We set the expected weights to the parameters that were used to obtain the synthetic data set. Finally, we call SGD and obtain the final weight vector and errors and weight vectors across all iterations. We make sure that the weight vector is a vector with shape 2 and its content are almost equal to the expected weight vector. You can see that the test passes, and finally we plot the learning curve from the errors across all the iterations obtained from SGD. You can see that the learning curve gradually decreases as we proceed through SGD iterations. And this actually tells us that with SGD we are able to make a progress and gradually move towards the minimum point in the law space.